Hello, whosoever you are. Today I will discuss about electric field on equatorial line of dipole. I will show you how to derive the relation for electric field on equatorial line of dipole. So for this we will consider an electric dipole consisting of two charges minus q plus q. So this dipole, its center is O. Let 12 be the length of the dipole. So we always take length as 12 so that when we solve numericals we try to avoid fractions for that. So 12 helps us to avoid fractions. So if this is the center of the dipole, this is 12. If this is center, this is L, this is L. Now let us consider a point at the equatorial line of the dipole. Equatorial line is perpendicular to the dipole moment. So let point P be on the equatorial line of dipole at a distance r from the center of the dipole. So we have to calculate net electric field on this point due to the dipole. Now you see this is L, this is R, and this is a right angle triangle. So hypotenuse will be under root R square plus L square. In the same way, this is also a right angle triangle. This is R, this is L, this is hypotenuse, it will be under root of R square plus L square. So now at this point P, we always assume a positive discharge. So to derive this equation, derive these formulas, we always assume a positive charge. So this negative charge will attract it and the field will be in this direction. This will be the direction of electric field. Let us take this field as E1. This is E1 due to minus Q. Now plus Q will repel it and electric field will be in this direction. Let us name this field as E2. So now E1 electric field by definition, electric field E1 is the source charge upon 4 pi epsilon naught the distance square. So distance between the points is under root R square plus L square. Distance square. This is by definition of the electric field. Similarly, E2 due to plus Q will be again Q upon 4 pi epsilon naught under root of R square plus L square whole square. So we have to calculate the net electric field now. Since we know that electric field is a vector quantity, so algebraic addition doesn't work here. In order to calculate the net electric field, we have to vector sum them. Now to do the vector sum, let us assume this angle to be theta. If this is theta, this line here is parallel to this line. This is theta. This line here, we will take the rectangular components of both electric fields. That will be the easiest way to vector sum them. This E1 has two rectangular components. One in the direction of theta, that is E1 cos theta. One perpendicular to it, which will be E1 sin theta. You always know in the direction of theta there comes cos component. When we do the rectangular components for a vector, see, this is actually, this is line, this is parallel line to it, this is the transversal. So if this is theta, this is theta. Now this side and this side, they are equal. So if this is theta, by the definition of isosceles triangle, this is also theta. Here again, this is line, this is parallel line, two parallel lines, this is a transversal. So if this is theta, this is theta. Now if this is theta, this line and this line, they are cutting each other. If this is theta, because of the vertical opposite angles, by the definition of vertically opposite angles, this is also theta. So we got the theta, we can do the rectangular components for E2. In the direction of theta, there will be E2 cos theta, and perpendicular to it will be E2 sin theta. Now as you see, E1 and E2 are same. So instead of this E2 sin theta, I can write E1 sin theta. So these two components will be E1 sin theta upwards, E1 sin theta downwards, and they will cancel out each other. And in the direction, in this direction, there are two vectors. One is E1 cos theta, another is E2 cos theta. So overall net, what remains here, net electric field remained, it is E1 cos theta plus E2 cos theta. As you can see here, E1 and E2 are nothing but one and the same. So instead of just E2, we can write E1 cos theta, and the formula will become twice E1 cos theta. Now instead of just 1 by 4 pi epsilon naught, we will write K for our convenience. So I can write this as E1. Instead of E1, I can write twice K Q upon under root R square plus L square. Now cos theta, you can get it from the right angle, the triangle here. Cos theta will be base upon hypotenuse. The base is L upon hypotenuse is under root of R square plus L square. Actually here, this root gets cancelled with the square here. Square and root cancel, so it is not under root, it is just R square plus L square. Now as you know, for a dipole, either charge of the dipole, because both are one and the same, and in case of an electric field, the sign doesn't matter. For potential it matters, but for electric fields, sign doesn't matter. So either charge multiplied by the length of the dipole, this gives us the dipole moment. Dipole moment P, again a vector quantity, as it has a direction from minus q to plus q. This is the direction of dipole moment P, and our net electric field came in this direction, opposite to the dipole moment. So overall this equation becomes 2ql. Instead of 2ql, I can write dipole moment, it is k times P upon, this is power 1 by 2, this is power 1. So total it becomes 3 by 2. Now, for an ideal dipole, the length 12 of the dipole is very small as compared with the this distance of point from the center. So L is very small than R. So this L square, it doesn't change much. So it can be neglected. So it has no effect overall on the equation. As this length of the dipole is very small, we can cancel it. So L square can be neglected. Here remains R square power 3 by 2. 2 and 2 cancels. Net dipole moment becomes net electric field becomes Kp upon R cube. Greater the dipole moment, greater is the electric field. Greater the distance of point from the charge from the center, smaller is the electric field. And this dipole moment direction is opposite to the direction of dipole moment. We can write in this direction as well. It is P times instead of K we will write 4 pi epsilon naught R cube. So this is the dipole electric field, net electric field on equatorial line of dipole. Thanks and whatever get lost.